Next is control charts for attributes. For variables that are categorical as opposed to continuous, like measurements and temperature, those were variables that are continuous, and the charts that we use for those are X bar and R charts. But when we have categorical variables, like whether it is good or bad, or defective, non-defective, yes or no, acceptable, non-acceptable, when that is what we are measuring, then what we could do is count the measurements, or we can compute proportion of those measurements. So how many defectives are there, or what percentage of the sample is defective. Okay, when you have situations like that, then the control charts are called control charts for attributes. And there are two control charts for attributes that we will be looking at. One is percent defective, which is P chart, and number of defectives, and that is C chart. So P chart, the formula is given here, which again looks like a confidence interval formula. So P bar is the mean of the percent defective from samples. So you'll have 1 P from each sample, P meaning the proportion of defectives from first sample, proportion of defectives from the second sample, proportion of defectives from the third sample, and so on. You average all of them, you get P bar. And then you plug the P bar into this, you get sigma sub P hat, that is the estimate, and then you apply into this formula. And Z again, you'll use 3 for 99.73% interval, or equal to 2 for 95.45% control limits. So here is an example. Suppose we have data entry errors that you want to monitor, and out of 100 entries, okay, you take a sample of 100 entries, how many defectives were there, or how many errors in the data entry records were there. 6 records had errors. There are 6 errors. So 0.06 is the fraction of defective. And then after a lapse of time, you take a second sample. Okay, this time again 100. Same sample size should be taken. And then 5 were errors. Okay, and so on. So now we have 20 samples, and we have percent defective from each sample. Now if you take an average of all of this, that will give us P bar. Okay, there is an easier way of computing that P bar. Instead of adding all these up and dividing by 20, we can divide the total number of errors, which is 80, by the total number of records. There were 100 records in each sample, so 20 times 100 in the denominator will give you P bar as well. So 80 divided by 100 is the sample size times 20 samples gives you 0.04, and plug that into the sigma sub P hat formula, and you get the sigma value. Now use Z equal to 3, then you get the limits. Actually this limit is 0.04 minus 0.06 will give you negative 0.02, but proportions cannot be negative. So when the formula works out to be a negative number for the lower limit, you should not just leave it as a negative number. That would be wrong. So you have to then round it up to 0. So when you plot it, you see that this point makes the data entry problem out of control. There is a possible assignable cause present. Now control chart for C is developed using Poisson distribution, and the formula is pretty simple. C bar plus or minus Z times square root of C bar, where 3 is because we want 99.73% control limits. If you wanted 95.45, then this will be equal to 2. So suppose we have a cab company that keeps track of number of complaints that the cab company receives from its rides. So here we don't have the individual values, but we have over the past 9 days a total of 54 complaints. So each day you have only number of complaints, so there is no proportion here. So this is a C chart. When you cannot compute a proportion, then it is a C chart. So that gives you 6 complaints per day, and then you do C bar plus 3 times square root of C bar, and the lower limit 6 minus 3 times square root of 6. Now again, this number, if it turns out to be a negative number, the count cannot be negative, so you have to round it up to 0. So here is how the plot will look like.